Welcome back. This is Mr. Wakefield, and we're going to learn about something completely new and different today here in section 9.3. Logarithmic functions, or logs for short, is what we usually call them. And in order to explain what a logarithm or a log is, let's take a look at a combination of what we've learned in the last two sections. In section 9.1, we learned about these exponential functions where you got, for example, 2 to the x, or sometimes you might have 3 to the x or 4 to the x. But we also learned in section 9.2 about how to take the inverse of a function. So putting those two concepts together, suppose I asked you to find the inverse of this exponential function. What would you do? As we learned in 9.2, we first of all changed the f of x to a y. Okay, and then we would interchange the x and the y. So there you go. That's the second step of finding the inverse. And then here's where we're stuck, okay? We've never been asked before to find, we've never been asked before to solve for a variable that's stuck inside of an exponent. This is the first time we've been asked to do that. No, you cannot divide both sides by 2, and the reason why is because this is not 2 times y. It is 2 to the y power, a completely different thing. And so we're kind of stuck, and so mathematicians many years ago realized this, and so they had to figure out a way to rewrite this problem so that the y would be by itself. And they invented a brand new type of function called the logarithmic function. So what they did was they wanted to get the y by itself. And so what they did was they called it log. I'm not sure why they called it that, but that's just what they call it. But what they do is they take it. There's 3 different components to the previous step right here. There's the base. Remember, again, a base is something that's taken to a power. You'll be hearing me say that a lot in this section here. The base is 2. Now, of course, the y is the exponent, and then the x then is the answer that you get when you combine the base and the exponent together. So rearranging stuff here in order to get y by itself, what they do is they say log or log. They put the base underneath the g, okay? Notice it's not on the same level as the g and the x here. It's a little bit below, so we don't get it mixed up with the log and the x. All right, so that's the base down below, and then next to that, but notice that the x is next to the 2. It is on the same level as the log, so you don't get it confused with the 2. But that is the answer that you get. You always put the answer here, the answer that you get when you take the base and the exponent together. That's what goes there. All right, next to the base, but a little bit above the base there. All right, and then the exponent is always what the entire logarithm is equal to. All right. So every logarithm, you guys, has 2 components to it. Okay, you can't just write down log by itself. That makes absolutely no sense, all right? Anytime you write logarithm, you've got to have this thing right here. We call that the product term, all right? That's what I'm going to call it. Other teachers call it different things. It doesn't really have an official name. But the product term is what you put here, and the product term is the answer that you get when you combine the base and the exponent together. So that's what we're going to call the product term. But every logarithm has to have a product term because it has to have an answer. All right, when you have a base and an exponent, okay, you got to have an answer. All right, and so how would you know what the exponent was if you didn't have an answer to refer to? For example, let's take a look at this example right here. Notice that 3 is the base because that's the thing that goes. That's the thing that goes underneath the g there, and then this is the answer that you get. So what they're asking here, let's pretend like we don't know that the answer is 2 yet. Okay, let me erase that. How do you know the answer is 2? It's because so if the base is 3 and this product term, which is the answer that you get when you combine the base and the exponent together, if that's 9, then what they're asking here is what is the exponent? Here's the thing, you guys. A logarithm is an exponent. It is always equal to the exponent that you get when the base is equal to this number underneath the g, and then the answer, which we call the product term, is right here next to the base, but risen up from the base here, written up a little bit higher. Okay, and so the answer must be 2 then, because 3 to the second power is 9. So again, a logarithm is an exponent. All right. And that's the reason why, because you can't have an exponent, you guys, unless you have 2 other components. You need to have a base and you need to have an answer, which again we call the product term. All right. And so that's the reason why I don't ever want to see anybody write this right here by itself. Log by itself means nothing in a math class. Okay, in your English class, you're talking about a log cabin or something like that. That's a different story. Then you can write log. All right, but in a math class, log means nothing. All right, unless you have these other 2 components. All right, now sometimes this component right here will be invisible, but it's still there. And I'll talk about that here coming up in a little bit. But you always have, sometimes this will be invisible, but either way, it's still going to be there even when it's invisible. So you have to have these 2 components, and the product term will never be invisible. All right, you got to at least have that visible. And so logs by itself mean nothing. All right, but logarithms are always equal to the exponent. Remember that. Log is exponent. All right. So one other thing I want to point out. If 2 to the x has an inverse, and we figured out the inverse of this, it ended up being y equal to this log. So if 2 to the x has an inverse of log base 2 of x, and you see I wrote that here, all right, you don't need to write that down right now. I was just helping you understand where logs come from. Not important to write all this down yet. If you did, that's even better though. But in a similar way, you guys, if that's true, then it would also make logical sense that if 3 to the x was your original function, then the inverse would be log base 3 of x. And if 4 to the x is your original function, then log base 4 of x would be the inverse, and so on. All right. Same idea works over here when the base is between 0 and 1, just like when we were talking about those types of things in section 9.1. All right, if f of x is equal to 1/2 to the x, then that means that f inverse of x would then be log base 1/2 of x, like that. All right, so that is going to help us later on when we talk about the inverse graphs again, just like we did before. But for now, you guys, I want to practice with you about these logarithms a little bit more. All right. So let's jump right into it, and we'll come back to that graphing stuff later. Going down here. What does this say? It says evaluate it, meaning figure out what the entire thing is equal to. All right, this whole thing is just equal to a log, because a log, remember, always has these 2 components, the base and the product term. And so they just want to figure out what the entire logarithm is equal to. All right. If you have a log with base 6 and product term of 36, what they're asking is this. They're asking 6 to what power is equal to 36. 6 to what power is equal to 36. All right, so what you want to do is you take your product term and you ask yourself, okay, how can I rewrite that product term with 6 and an exponent? All right, well, we know that 6 to the second power is equal to 36, so you can rewrite the 36 as 6 squared, and then that makes it obvious that the missing exponent here is 2. All right. And so the answer is 2. All right. Again, the question was 6 to what power is 36? So I realized that 36 is 6 to the second, so that missing exponent is 2. That's how it works. Let's try that again. Here the base is 2, and the product term, which again is the answer that you get when you combine the base and the exponent together, that is equal to 8. So what they want to know, because remember, logs are exponents, right? They want to know, since they are asking you to evaluate the log, they want you to figure out what the log is equal to, and that means to figure out what the exponent is equal to. Okay, so 2 to what power is equal to 8? Well, if I rewrite the 8 as having a base of 2, what would be the exponent? The exponent would be, wouldn't that be the third power? Isn't it true that 2 to the third power is equal to 8? And so that must mean that the missing exponent here is 3. Okay, and then we can continue on with this now. All right, what about problem number 3 right here? There we go. It is asking what? It is asking 6 to what power is equal to 1/6? Okay. What I want you to do here is I want you to, whenever you get a fraction as your product term, and especially if it has a 1 on the top, I want you to remember this property that we had back in chapter 1. Property said what? It said that if you have 1 over a to the n, all right, that is the same thing as a to the negative n. So if I can put a 6 down here on the bottom to a power, all right, what would that be if we then converted it to this? And we'll get into that. So that's the approach that I'm going to take, though. All because we have a 1 on the top. So if you've got a product term with a 1 on top of a fraction, okay, we're going to try to rewrite the bottom so that it has the same base, and then we can use this formula. Let's try that. Okay, as you guys know, 1 over 6 is the same thing as 1 over 6 to the first. So I took the bottom and I rewrote it so that it had 6 to a power, because that's the base that we want. We want 6. All right. Once you do that, you then realize that, oh, hey, 1 over 6 to the first is the same thing as 6 to the negative 1. And so that must mean then that the missing exponent is negative 1. Okay? Let's go on into the next one here. In problem D right here, it's a similar thing where once again you have a product term with 1 on the top. Since we have a 9 on the bottom there, I want to take and let me set it up here first. Your base again is 3. Your product term is 1/9, and since they want to know what the log is equal to, we have to figure out what the missing exponent is. Again, just like in the last problem, we want to take the bottom, since the top is 1, want to take the bottom and rewrite it with the same base as we have here, which is 3. As you guys know, that is 3 to the second. 9 is 3 to the second. And since you have 1 over 3 squared, using that same rule that I showed you from chapter 1 just a moment ago, that's going to be 3 to the negative 2 power. And so that must mean that negative 2 is the missing exponent. Okay. Remember, you want to rewrite the product term so that it is not 1 over something, but you want to ultimately write it where you just have the base, and it has to be the same base, of course. You want to rewrite it so that it has the same base with an exponent, but just those two things, the base and the exponent, okay, so that then you can then reason that the missing exponent is negative 2. They don't want to know what 1 over 3 to the power is. They want to know what 3 to the power is so that it's equal to 1/9. Well, 1/9 is equal to 3 to the negative 2. All right. They don't care about 1 over something. All right. They want you to ultimately convert it so that it's 3 to a power so that you'll then know what this missing power is. Just want to make sure that's clear. All right, so you need to convert your product term so that it's the same base along with an exponent, but nothing else. No 1 on top of that. All right, so let's keep going here. Whenever you have a product term, and let me set it up here first as I'm talking about it, but whenever you have a product term that is the square root of the base, for that logarithm. Okay, we got square root of 6 and we got 6. What that means is, if you go back into section 7.2 real quick here, we know that the square root of something is the same thing as that same number underneath the radical if you take it to the 1/2 power. All right, here's a look at it right here. 9 to the 1/2 power is the same thing as square root of 9. All right, in the same way, 6 to the 1/2 power would be the square root of 6. And that's exactly what we have here. So once again, doing the same thing we always do here, taking the product term, which is square root of 6, and rewriting it so that it is equal to a base and an exponent with the same base as we already had here for the log 6. All right, we now realize that the missing exponent must be 1/2. Make sure that your answer that you circle is the exponent, you guys. All right, don't circle 6 to the 1/2. All right, they want to know what the log is equal to. The log is equal to the exponent only. All right, so make sure that you circle the exponent that you found. So, setting this up once again, we got 3 to some power that we're going to figure out is equal to 1 over square root of 3. This combines what we've done in the last couple of problems here. If you've got a 1 on top of your product term, try to rewrite the bottom so that it is 3 to a power, because 3 is your base here. Sure enough, as we just learned, square root of 3, if you make it into an exponent, that is 3 to the 1/2, just like square root of 6 is 6 to the 1/2. All right, but they don't want to know, they don't want that 1 there. They just want to have 3 to a power. So as you guys now know, 1 over 3 to the 1/2 is the same thing as 3 to the negative 1/2. All right, so the missing exponent must be then negative 1/2. Let me write that down and circle that because that's the answer. The exponent is the answer. All right, next one. Same idea here. Notice it's 7. Isn't 7 the square root of 49? Okay, and since it is the square root of 49, as I set this up, then it's just like problem E. It just looks a little bit different. All right, since 7 is the square root of 49, then we know that the missing exponent must be the 1/2 power. Okay, because like I said in problem E, if you have a product term that is the square root of the base, then that missing exponent must be 1/2, because the base to a 1/2 power is supposed to be equal to the product term here, and sure enough, it is equal to the square root of 49, which is 7. All right. So 7 is the square root of 49. We know that 49 to the 1/2 power is equal to the square root. And so that missing exponent again must be 1/2. And finally here, if your base and your product term are exactly the same, all right, then the missing exponent must be 1, because you know that if you take a base to the first power, it will be equal to the same thing. So if the base and product term are the same, the missing exponent must be 1. Okay, sorry, I forgot to write down the answer on the last problem here. Let me go back over there as well. That was a missing exponent of 1/2, wasn't it? Okay, so there we go right there. Here we go right there. And that is logarithms, evaluating logarithms. All right. Let's take a look on the back here, see where we're at here. Okay, so let me go back to the front. I want to look at some general properties here. Some of these we already understand already. Look at number 2 right here. It says here that in number 2, if your base and your product term are the same, then as we just found out, the missing exponent must be 1, and that's why the logarithm is equal to 1 when you have b and b right there. Base and product term are exactly the same. Okay, something we haven't talked about yet, though, is that if your product term is 1, what are they asking there? They're asking b to what power is equal to 1. b to what power is equal to 1. Okay, well, this is not true with every single base that you'll ever have, but when we do logarithms, we're only supposed to do positive bases not equal to 1. Similar to what we talked about with bases in section 9.1, it's the same thing. All right, so when you have bases like that, positive constant numbers not equal to 1 are going to be your base. In that case, there's only one exponent that will work if your answer, or your product term, in other words, is 1, and that would be an exponent of 0, because you know that when you take something to the 0 power, it is equal to 1. Okay. Property number 3. Property number 3 here is saying b to what power is equal to the product term b to the x. Well, you can see right there that if you have b to a power and b to the x, the missing exponent must be x, because then these two things would truly be equal, bx and bx. All right. So when you have a product term that already has a base in it, then whatever the exponent goes with it will also be your answer. Okay, so if you've got a base, for example, let's say that base right there was 3, okay, and then inside of the product term you had 3 to the second power, let's say, for example, then that must mean that the power is your answer. So 3 and 3 to the second would then give you an answer of 2. All right. And then finally here we have a log stuck inside of an exponent. And if you look closely on your worksheet, I know it's kind of hard to see here on the screen, it's so small, but the base that goes with the log, and again the log is stuck inside the exponent this time, it's not by itself on one side of the equal sign, it's stuck inside the exponent. If that base of that log is the same as the base right here, the big B, all right, then the answer will be the product term inside of that logarithm. That's what that one's saying. All right, and so that is those 4 properties. As I'll explain here in a few minutes, these properties over here are extremely similar. Don't worry, they're not completely different. Okay, and so that'll make it easier to deal with those. All right, since they're so similar to these ones that we've already talked about. Let's flip this over. You'll see here that based on what we just learned, we can now use that to help us with these problems right now, because you know, as we just learned a moment ago, whenever you have a product term of 1, the answer's got to be 0. You don't have to write down the work right here, but I'm going to here just for practice. This is asking 6 to what power is equal to 1, isn't it? But when your product term is 1, all right, the only way that that can happen in this situation is if the exponent is 0. So if you make it, like always, if you make it the same base, the product term is the same base as the base you started with here in the log, which is 6. The only way that'll happen is if that exponent is 0. As we learned in the third property on the front side of the worksheet here that I'm circling right now with my pencil here, okay, we know that when you have a product term that has a base and an exponent, but the base of that base and exponent is the same as the little base underneath the g, then this is going to be equal to 6. All right, why is that true again? It's because the question is asking 4 to what power, because that 4 underneath the base or underneath the g is telling you what the base is, and then it has to be equal to the product term, which is 4 to the 6th. And so the only thing, sorry that fell off of there, so the little 4 is your base, the product term is 4 to the 6th. Since the bases are the same here, okay, then the missing exponent must be 6. Okay, if you let me just write this down. If you have an equation here, which I've created here on many of these problems, if you have an equation where you just have a base and an exponent on each side of the equal sign, but the bases are the same, 4 and 4, for example, then the exponents must be the same if the bases are the same. But that's only if you just have a base and an exponent on each side. If you have additional stuff on the left or right side, that's a little bit of a different story. But if it looks exactly like this, where the A and the A are the same, in this case 4 and 4, then that proves that the exponents have to be the same. And so that means that missing exponent has to be equal to 6, because the b has to be equal to c when this happens. When you get an equation like that, the b and the c have to be equal to each other. All right. Just wanted to clear that up as well. This one here is the last property. Last property right there. It says if the big B and little b are the same right there, then the product term of that logarithm is going to be equal to the answer. So again, if you look at your worksheet closely, because it's kind of small on the screen here, the big 5 is the same as the little 5 right there. There is a little 5 right there next to the log if you look at that. Okay, and so that means that the answer is 17. All right. Okay. Okay, before I move on to the next problem, I want to show you those other properties on the front, which, as I promised, are very similar to the first set of properties. Please notice, first of all, that whenever the base is invisible, you see how we have a log right here, but there's no base underneath the g? When that happens, as we've seen in a lot of areas of math, a lot of times things are invisible in math. In the case of a logarithm, when you have nothing underneath the g but you just have a product term, that automatically means that the missing base is 10. It is 10 and only 10. It's nothing else. All right. So if you look at these 4 original properties, all right, on the left-hand side of the equal sign, it looks exactly the same as these 4 things that are on the left-hand side of these equal signs. It looks exactly the same except for the base is missing. So understanding that the missing base here is 10, all right, these things now are exactly the same as these ones over here. Notice that we have a product term of 1, so it's going to be 0, no matter what the base is. Okay, if you have, and you don't have to write this down as long as you know that it's 10, but if you write the 10 in there, which is also okay, you can make the 10 visible if you want. See how the 10 and the 10 are the same? And we learned over here that when the 10 and the 10 are the same, it's equal to 1. All right. So again, it's saying the same thing that this says. All right. When you realize that the invisible base is 10 right here, whether you write this down or not, right here underneath the g, if you have 10 and 10 to the x, the answer's got to be x. That's what this is saying right here. If the b and the b are the same, the answer's x. If the 10 and the 10 are the same, that's exactly the same thing. All right. And finally, if you have 10 and then log base 10 of x, again, there's an invisible 10 there underneath the g. All right, then just like what this says right here, where the b and the b are the same, the answer is x right there. All right, so this thing right here, these statements, all 4 of these equations are exactly the same as these ones right here, just so long as you understand that when the base is invisible, it's 10. And so you don't need to learn a whole new set of properties here. You just got to know that the invisible base is 10. And then if you know that, and then you know these 4 properties, then you don't need to learn these properties. All right? You already know these properties automatically if you know the invisible base is 10 and if you know these 4. Okay? In a similar way, we have another one over here called the base e. Okay, e is actually a constant number. It's kind of like I, okay, where I is equal to the square root of -1. It's a letter when you write it, but it's equal to a constant number, so it's not a variable. Variables change from one problem to another. E will always be equal to approximately 2.71828. Okay. Don't worry, you don't need to memorize that number right now, okay? Just know that it really is equal to that. It is equal to a constant number, okay? But it is a very commonly used number going forward in future algebra classes if you were to take them, okay? And so that's why we learn about it. But what happens is that if we ever want to do log base e, because e is such a commonly used thing going forward, all right, instead of saying log base e, they come up with a new name that's easier to write. It says ln. ln. Okay, so whenever you have ln, that's the same thing as log base e. So log base e of 1. We know that anytime the product term is 1, the answer is 0. I'm just repeating the same thing that we had over here in the first properties. All right, so again, if you know these properties and you know that ln means log base e, then you don't need to learn a whole new set of properties here. You already know these automatically. Let's try it again here. See how it says ln of e, which is the same thing as log base e of e. All right, but because you already know that when b and b are the same right here, it's equal to 1, you know that log base e of e is equal to 1, and therefore you know that ln of e is equal to 1. So if you, again, like I said, if you know this property already, and you know that ln means log base e, then you know that this is equal to 1 without having to learn a whole new thing here. All right, same thing here. This is log base e of e to the x. I have that written over here. Log base e of e to the x. All right, again, you don't have to write this out right here. I'm just writing it out so you can see what I'm thinking. Okay, as long as you know that ln of e to the x is the same thing as this over here, okay, then you know that the answer is x, because when these two things are the same, in this case e and e, all right, when those two things are the same, though, the answer is x. And same thing here, all right, e and then log base e of x. When the big E and the little e are the same, the answer is x. So again, these properties are something that you already know if you know that ln means log base e, as long as you also remember what these properties are. So you just need to learn and make sure you know these 4 properties, and then if you know that the invisible base with the log is 10, and you know the invisible base with ln means log base e, all right, then you're good to go. All right, then you know everything here in this chart. Okay, with these 12 equations, you know them all now. If you know those things. All right, so moving forward here, going on to the back again. Let me pull that out here. So, with that in mind, we know that the invisible base right here is 10, and so you can use that property on the front right here that says that log base 10 of 10 to the 5th power is 5. You could do that property, or if you choose to do it the long way, you could say, hey, I know that the 10 underneath the g, I know the invisible base underneath the g is equal to 10, and I know the product term is 10 to the 5th, and so I know that 10 to what power is equal to 10 to the 5th. That's how I set up a logarithm when I need to figure out what the logarithm is equal to. Okay, I take my base underneath the g, and I take my product term, I put it over here, and then I'm looking for the missing exponent that goes with that base that's underneath the g. So either way, you're going to get an answer of 5, aren't you? Whether you use that property or you do it the long way, either way you are. Okay. So yeah, you don't need to write this out if you use that third property, all right? I will just accept 5 as an answer. You don't need to show the work on that because, again, the property that I asked you to learn will tell you that automatically. Same idea here. You don't have to write down this step right here that I'm doing because it's already a property, but just to emphasize that ln is the same thing as log base e, all right? And we know that when you have e and e right there, then the exponent that goes with the e is going to be your answer automatically. So the answer is 4. Next one here, we have what? We have 10 to what power? There's no property for this one. Okay, there's no, if you look at the properties, nothing fits into this here. 10 and 100 are not the same or anything like that. But we do know that, just like we did on the front side of the worksheet, you take the product term and you try to rewrite it with 10 as a base. And if I do that, I get 10 to the second, don't I? Because 100 is 10 to the second. Okay, so just like we talked about up here, if you have 10 to the question mark power and 10 to the second power, then since the 10s are the same, then the exponents must be the same as well. And so therefore, the missing exponent must be that same exponent over here too. Okay. Next one here, what is it saying? Since ln is the same, and I'm just going to write this down just for practice. You don't have to do this, all right? What's important is that you know that ln means log base e, okay? So what is that asking for? It's asking for e to what power is equal to 1 over e to the 7th. Okay, and just like we did on the front of the worksheet, if you have 1 on top of your product term, all right, you try to make the bottom to have the same base as over here. Well, the bottom already is the same base, all right? So I just need to, excuse me, I just need to realize that 1 over e to the 7th is e to the negative 7. And so now I know that the missing exponent is negative 7. Okay. And finally here, again, you don't have to write this down, but just to emphasize it, since we're learning this for the first time, ln of 300 is and I'm sorry, I wrote down 100 by accident. Ln of 300 is the same thing as log base e of 300. And we know that when big E and little e are the same right there, then according to property number 4 on the front, and we can look at the E version of that, when those two E's are the same, the answer is going to be this number right here next to the second E, which of course is 300. Okay? And so your final answer there is 300. Okay, so go ahead and try out those next 8 problems right there, and when you're ready to look at the answers, hit the play button again. All right, number 1 right here. We have a base of 7 and a product term of 49. So again, we want to take the product term and try to rewrite it as a problem that has 7 as a base. And so since 49 is equal to 7 squared, then that must be the missing exponent right there. 2 is the answer. All right, moving forward here, number 2. Again, same idea here. 2 is your base. 8 is the answer or the product term. What's the missing exponent? Well, since 8 is the same thing as 2 to the 3rd, 3 then is your missing exponent. Moving forward here to number 3. Again, there's that thing where the product term has a 1 on top of the fraction, and so we focus on the bottom, try to make that the same base as the base that you're given in the problem, which is 3. And since we have 1 over 3 to the first, that means that we have 3 to the negative 1 equal to the product term. And so therefore, the missing exponent is negative 1. Number 4. 81 again is such that the product term is the square root of that, and as we saw on the front side of the worksheet, if your product term is the square root of your base, then you can then realize that that is 81 to the 1/2 power. Again, the square root of something is the same thing as that same something that's inside of the radical taken to the 1/2 power, as we learned in section 7.2. And so therefore the missing exponent is 1/2. Down here in number 5, okay, anytime your product term is 1 in a logarithm, your missing exponent will be 0 every time. Number 6 again is similar to I don't need that bracket right there. Similar to number 4 right here, where your product term is the square root of the base, and so that means that the missing exponent, just like a number 4, is going to be 1/2. Here's that property, and again, you could write it this way, the long way, or you could just realize that, hey, my base is the same as the base inside the product term. Okay, so you got log base 10 of 10 to the 8th. When you have that, as we said, that means, and I was going to show you here the property just a moment. although I'm sure you already have it in front of you. But and you can look at it over here, log base 10 of 10 to the x, just like log base b of b to the x, that is equal to x. And so that means that whatever the exponent is with that bigger 10 right there, the second 10, that would be your answer. So since it is 10 to the 8th, it's 8. Okay. Number 8. It's that final property right there where you know that if the big 7 and the little 7 are the same, then the answer is the product term with that goes with the little 7 right there, 23. All right, so that is evaluating logarithms, okay, and assorted properties that go with that. What I'd like to do right now, and let me pull out a clean sheet of paper here so we could do the work by hand again. But in these next two problems right here, it asks for the domain. We've done this before where they give you f of x and they ask you for the domain. We did it in chapter 2 when you had problems with fractions in it. Okay, and we had to look at when the denominator was 0 and all that kind of thing. In chapter 7, we looked at the same problem. Let me pull it up right here, where you had the square root. And because we can't have imaginary numbers when we do f of x, we're just doing real numbers. All right. Normally, anyway, at least in this class, our f of x's are only real numbers. So, therefore, the inside must not be negative, and therefore it has to be greater than or equal to 0. That's for square roots when you are asked to find the domain of f of x. Okay. And so that's why we say greater than or equal to 0. Well, as it turns out, you guys, when you have f of x equal to a logarithmic function, and I'll talk about this more in the next section, but when you have a bracket, by the way, just before we get into domain, when you have a bracket next to your base right there, that entire bracket is your product term. Not just the x, but the entire thing. If the bracket was not there, then just the x would be your product term, okay? But with the bracket, it's the entire thing, x plus 6. Okay, as it turns out, you guys, when you have a product term of a logarithm inside of your f of x function, it is required that the product term, x plus 6, is greater than 0. Not greater than or equal to 0. That's where it's different from those radical problems I just showed you. It has to be strictly greater than. No alligator feet there. Let me show you why. Remember, product terms, you guys, are the answers that you get when you take 5 as your base, and then the entire logarithm, which would be the... In fact, let me write this down. You don't have to write this down. This is just going to help you understand better. But if you have y, which is the same thing as f of x, when you have y as your equal to your logarithm here, that means what? That means that 5 is the base, y is the exponent, because the entire logarithm is equal to the y, and we know that logarithms are always equal to exponents. So 5 and y are the base and the exponent, and then the product term is always the answer. When you put the base and the exponent together, it's always equal to the product term. Okay, now why does that mean that x plus 6 has to be greater than 0 for? Here's the thing, and you can write this down. I'll go ahead and write it down right here. A positive number, a positive base, you guys, like 5. It doesn't matter what kind of positive number it is, as long as it's positive. If you have a positive number with any exponent, okay, this could be any number at all. That exponent, it could be positive, it could be negative, it could be 0, any number at all that would go inside of that y right there. If you have a positive base, you guys, it always has to be positive. If you take any positive number and you raise it to any power in the world, even if it's negative, okay, the answer will always be positive. Try it, okay? Even if you take like 5 to the negative 1 million power, that's still going to be a positive answer, because it would be 1 over 5 to the positive 1 million power, okay? And so that would still be positive divided by positive. All right, so this is just explaining right here. This thing right here is explaining why your product term can never be anything other than a positive number, because it's the answer that you get when you combine the base and the exponent together, 5 and y. Okay? It always has to be positive. So that's the reason why when you get a logarithm in your function and they ask for the domain, you need to make sure that the product term is positive. And that's why I'm going to now solve this inequality in order to figure out what numbers make that thing positive, and then we'll be able to figure out the domain. And that's all you need to do, because there's no denominators to worry about. Okay, so you don't need to do anything with that when we do like we normally do when we're doing the domain. No denominators to worry about, no radicals, no square roots to be concerned about like we saw in this example here. So the only thing you got to do is make sure that you come up with numbers. The only thing you got to do is make sure you come up with numbers that make that product term positive. All right, this is a linear inequality. As we learned in section 4.1, linear inequalities, because it's just x and not x squared, all right, and it's a polynomial on both sides, linear inequality is what we got, and that means that I'm going to move the 6 over with the 0, and I get x greater than negative 6. When you give the x by itself in a linear inequality, unlike the inequalities you saw in 8.5, those ones are more detailed. You just need to put the number on the number line and then figure out what side it is shaded on. Okay, this is just with linear inequalities. All right, again, review section 4.1 if you need to for that. But as we learn with linear inequalities in 4.1, once you put your number on there, negative 6, after you get the x by itself, bring that number down. But then the side that you shade, it will always be one side with linear inequalities, one side shaded, the other side not. How do you know which side is shaded? You know because of the alligator. If the alligator's eating the variable, then that means that the variable must be greater than, and greater than means we go to the right. If the alligator had been eating the negative 6 instead of the x, okay, that means that the variable would have to be less than, because the negative 6 would be greater than, and then you would go the other way, to the left, in the less than direction. What do we do after we do our shading? We put our bracket on there, and since the alligator doesn't have feet right here, we're going to use a round bracket. So I did my shading, I did my bracket, all right. Always do a bracket when you have a shading on one side of a number but not the other, like we have here with negative 6. And then as the directions say, interval notation. That means what? That means negative 6 is where the shading starts. It ends at positive infinity. And put your brackets in there as well like we normally do. Okay, negative 6 is round and infinity is always round. Okay. So that's problem A. The other one's similar. Okay, it's just additional practice. So you do it the same way. Okay, since there's just a since you have a logarithm and then you have there's an invisible 10 right there, right? But next to that invisible 10 is a bracket. That means that entire parenthesis is your product term, so we need to set that greater than 0. This is a linear inequality, again, for the same reason as the last problem. So we move over the 2, but we also got to divide out the negative 1. But what do you guys, when you divide by a negative in an inequality? You have to flip the alligator, don't you? Okay, flip the alligator mouth the other direction. So we got x is less than 2, all right? After I put 2 on the number line, okay, again, you do the number line after you get the x by itself. Bring that number that goes with the isolated x right here, bring it down. And then what direction is the shading going to go in? With a linear inequality, it's going to be one or the other. One either this side or this side, but not both. It's going to be this end because the alligator is not eating the variable. That means that the variable is less than, all right, irregardless of what side the x is on. If the alligator is not eating it, that means that x is less than, and therefore we go in the less than direction. Again, we have a round bracket because the alligator doesn't have feet. So what's the final answer there? The shading starts at negative infinity, and it ends at 2. And so there's your final answer right there with the brackets. Don't forget those. All right. And so that is domain problems when you have a logarithm inside of your function. All right, that's how you want to approach it. Finally, one last problem here. It says graph 5 to the x. Well, hey, we already did that in section 9.1, but it asks us on the same grid, meaning on the same xy graph, go ahead and graph this as well. Well, here's the good news with that. This is the inverse of that. So if you want to graph a logarithmic function, what you can do, I gave you like this thing on the front side that you can refer to for graphing logs, and there's a couple different ones. All right, you don't really need to worry about this right now, though, because if you know, and you do, if you know what the graph of 5 to the x looks like, and you actually put that on your graph, all right, you just need to do what we did in the last section where you graph the inverse, because this automatically is the inverse of that. Okay, just like 2 to the x would have an inverse of log base 2 of x, 3 to the x would have an inverse of log base 3 of x, as we talked about earlier. 5 to the x that would then have log base 5 of x as its inverse. So this is actually f inverse of x. You don't have to write that down, but it reminds us that we can do that whole inverse strategy for graphing that we did in the last section. Here it is right here. These problems right here. We can do the same thing. So we'll get to that here, but let me go ahead and set up let's do the original function here since we know what that one looks like, and then we'll do the log graph. Since we don't know what that normally looks like, we can take what we learned in with the 5 to the x and go ahead and take the inverse of that and graph the inverse of it, and then that'll give us the log graph. So what is the, how do we graph 5 to the x? As we did in section, 9.1, we do -2, -1, 0, 1, and 2, and then we plug each one of those numbers into the x. All right, we get what? 5 to the -2. 5 to the -2 is equal to 1 over 5 squared, and that's where 1 over 25 comes from. All right. If you want to write that down, you can, again, just for practice. You don't have to. 5 to the -2 is 1 over 5 squared, 1 over 25. All right, there it is. What is 5 to the -1 if I plug in -1? That's going to be 1 over 5 to the first. All right, just the same thing as this, only the exponent is 1 on the bottom instead of 2. 5 to the 0 power, anything to the 0 power is 1. 5 to the first is 5, and finally 5 to the second is 25. As I promised you in section 9.1, you don't have to graph all 5 of these, so if you want to leave out the 25 since it's so big, so far off the graph, then you can do that. And by the way, the reason why that's important here is because you want the scale for both the x-axis and the y-axis to be the same. It has to be. It doesn't mean you got to do 1, 2, 3, 4, 5, but if you are going to change it to, say, 2, 4, 6, 8, 10, then the y-axis would have to be that way as well. I know I said that in other graphs you didn't have to do that, but when you graph an inverse graph on the same grid as the original graph, the x-axis and y-axis have to be the same scaling, okay? Excuse me. So, I'm going to go and just do the standard 1, 2, 3, 4, 5 scale. But that means that this has to be the same, and that's why I don't want to put that 25 on there. The 25 is way, way, way up here. All right. But these other ones I can fit on there. All right. 1, 5. is right here. 0, 1 is right there. All right. Negative 1, 1/5. 1/5, if you put that in your calculator, is 0.2. So just so long as you get it between 0 and 1, all right, that's fine. Same thing with 1/25. That is 0.04 into your calculator, if you figured that out in your calculator. So again, since it's 0 point something, just get it between 0 and 1. That's close enough. All right. So let's draw our normal banana looking shape here. All right, it's going to be a little bit more of a tall, narrow banana, because when the base gets bigger, as opposed to having, say, 2 to the x or 3 to the x like we usually had before, if it gets up to like 5 or 6, this banana shape is going to be very tall and narrow, like I said. So let me go ahead and draw that. But remember what we do with these banana shapes, you guys, all right? They have arrows on both ends, all right? Unless it's one of those ones where you multiply by -1 in the front of it, which this is not. It's going to go up fast on one end, and it's going to go down almost in a flat way on the other end. Okay. How do we do the inverse graph? We do the inverse graph by plotting that dotted line first, all right, just like we did right here in these problems. Okay, let's just look at it right next to each other here. How did I do that dotted line? I graphed the y-intercept as 0, and then I went up 1 and over 1 for the slope, just like I did here. Okay, up 1 and over 1, the slope is 1, and then I draw a dotted line. Again, it's got to be dotted. It's not meant to be a part of either the original graph or the inverse graph. It's just supposed to help you find the inverse graph. Okay. So there we go, right there. And then what did we say about inverse graphs down here in the previous section? We said that if these 5 points are your original points from the original graph, then for g of x, which is the inverse, okay, your chart then would be the same exact numbers, except for the x's and y's would be flip-flopped, wouldn't they? So you would get 1/25 and -2, 1/5 and -1. In other words, the same numbers as over here, but where the x's and y's are switching. So now we have 1 and 0 instead of 0 and 1. We have 5 and 1 instead of 1 and 5. We have 25 and 2 instead of 2 and 25. So again, you don't have to graph the big number there, 25, but if I graph the other 4, let's see where those are, and that'll help me. That'll help me draw the final shape here. 1/25, -2. Let me get -2 on here. It's going to be right here. Again, x is a fraction. If you put that in your calculator, like we said earlier, that is 0.04. So just make sure that since it's 0 point something on the x, make sure it's between 0 and 1. The 1/5 again is 0.2, so just make sure the x part of it is between 0 and 1. 1, 0 is right here. 5, 1 is right here. And again, don't worry about the point that has the 25 in it. Okay. Now, we have a basic guideline, but don't graph it yet. Let's make sure that the graph, as I mentioned in these problems before, make sure that the graph looks like you folded the paper over from the original graph, and then wherever it lands, that's your inverse graph. So we're going to do that right now. Again, just like this problem right here, your entire original graph is only on one side of that dotted line, so you just have to fold it once. Okay. If there was, like I said before, oh, I'm sorry, I'm looking at the wrong one there. Let me pull that out. I was looking at the answer for what we're trying to find out right now. I'm sorry about that. The graphs from the, but it looks so similar though that it's actually going to end up being almost the same thing as that. But this is what I was meaning to look at. These are the problems from the last section here, and now just the same way that we did it before. All right, you turn your paper so that the dotted line is going straight up and down vertical, and then just make this side look like it's folding over, and then wherever it lands on the other side, that's going to be your inverse graph. Again, you don't have to do what we did here in this first problem that we did in the previous section. I know you can't see the dotted line there very well. Let me redo that. But in this problem here, what we did was we did both sides, all right, of the original graph, and then we folded it over. From the left side of the graph to the right side was this red part here, and then the original right-hand side of the dotted line folded over to be the left side. Again, you don't need to do that here because the original graph is all on one side. But there are some problems for when you have f of x. If you have f of x equal to, say, 1/2 to the x or 1/3 of the x, then you'll end up with a graph that is on both sides, and you'd have to do something like you did here. But in this problem, you don't. Okay, you just have to, since it's only on one side, the original graph, just fold it over, and then wherever it lands is your graph. So let's just make sure it looks like that. You don't have to literally fold it over. Like I said before, you just have to make sure it looks like you did. Okay, as long as it looks like you did. And if you did fold it over, it would look like, speaking of looks, it would look like that. Okay, there it is right there. See how the two sides look like one side folded over to the other? All right, that's exactly what you want, like we saw here in the previous section 9.2. All right, so that's again how you do an inverse graph. And as we said, that second g of x function, that's exactly what that graph is. It is the inverse, and so doing the inverse graphing strategy will allow you to graph that g of x function. All right, so this one right here was f of x, these points right here, and then the g of x was in red. So that's how you graph a log function. You can graph it off of the original function from 9.1. So like, for example, if I said, I want you to graph log base 2 of x, then what you do is you would do 2 to the x, all right, over here, put that on the graph, and then just flip it over. Okay, do the dotted line and the flip over thing, the fold over. All right, so that's how it works. All right, and that concludes section 9.3. We'll have plenty more to talk about all throughout the rest of this chapter in regards to logarithms. We're just getting started with those, so you have plenty more time to get exposed to that and get used to logarithms in general. All right, but in the meantime, though, please let me know if you have any questions right away about this, because of the fact that we will be seeing more logarithms. You want to make sure that you understand the basics. Okay, so let me know. And in the meantime, though, you have a good day, and we'll see you at the next video.